try to somehow use the internal forces at these contact points to find the optimal geometry, or to find a geometry with minimum infeasibility actually. So the concave approach, because of its flexibility and have been more used in generation of new masonry assemblies, including interlocking assemblies. As you can see here, for example, in the middle, this is the method which has been developed by block research group in like the tool that they already have. Its name is Compass Crow, which tries to distribute a number, several numbers of contact points, and then try to find internal forces at that. And then the other one, which is actually the work which I've done before, also follows the same concept and tries to find the concave method, in which not only you can find the internal forces at interfaces, but also you can find the internal forces at what we call the interfaces, which means that we don't consider the blocks to be completely rigid, but also we can include the possibility of fracture and the inside the blocks, which is very important and fundamental when we are talking about interlocking concave assemblies, because of the concave geometry, the possibility of fracture is also important, and we cannot actually ignore that. So, but there are also some limitations related to concave approach, and basically one of the main limitation is about how to formulate the torsion shear interaction, because actually we can see that the torsion shear interaction, which as you can see here, for example, it happens when the lateral forces are applied at one interface with some eccentricity with respect to the centroid of the interface, and we can have combination of shear and torsion, and it appears that when we want to adopt the concave approach, then we face several limitations, and of course convex approach is much more robust and accurate way to do that. That's why I try to explore, but however, on the contrary, the convex approach has some limitation in terms of the geometry. For example, since now the formulations are limited to rectangular interfaces, and I try to explore if we can find the universal and simplified constraint for torsion shear to somehow define the torsion shear interaction as any planar but different interface geometries. So basically, this graph is something that you can usually see to explain the torsion shear interaction. This basically shows the maximum torsion and shear which an interface can sustain when the interface is subjected to lateral forces with different amount of eccentricity. And what we see is that when the interface is rectangular, this curve is always convex downwards, and then all approximation is based on that specific geometry that we can see here. We can observe that, at least for the case of rectangular interfaces, the convex method, which, as I said, the interface is just abstracted to one single contact point in the middle, is much more robust and accurate. And as you can see here, for example, this the graph corresponding the convex approach is more similar to the result that we found by experimental test, and the concave approach usually have several limitations, because finding the correct number of contact points and the location of the contact points is usually something that we can find through trial and error, and that can vary for different geometries of interfaces. For example, for the case of rectangular geometry, we found that if we use, for example, three contact points, then using that we can find relatively better the possibility of having a universal and simplified torsion shear interaction using the convex method. And the other reason I was exploring that is my other work that we try to find the best joint layout for uh, designing interlocking assembly. And the overall idea behind that is that we tried to find the best combination of what we call inner faces and dry faces, which can correspond the maximum uh, load bearing capacity. And to find that combination, basically application of convex method is much easier, because what we should do is simply to abstract a dry face to one contact point, inner face to one contact point, and of course it is much easier to adopt convex approach compared to concave approach. And that's why it's important to see if convex approach is capable to be extended to different geometries. If we are able to do that, then we can extend that method, for example, to different geometries. As you can see here, the idea behind that layout optimization is that we have a discontinuity, and then we try to find the optimal combination of interfaces at which the fracture within the block can happen, and dry interfaces. And this optimal combination, should correspond to the partitioning, the partitioned method discrete assembly with maximum load bearing capacity. So it's very important for extendability of the formulation to different geometries. So to be able to investigate that, first I demonstrate how this simplified constraint can be formulated. And for that, I start with pure torsion and pure shear cases that you can see here. And the idea is simple. The idea is that we just try to find the um, yeah, we try to find the torque caused by the shear or tangential resistance at any arbitrary point on the interface. These values together, and then presentazione numero 3, 2,
Sì.
3, giusto?
2. Diventa così.
Prova a vedere.
Mm-hmm.
Si vede sempre quella cosa.
Sì, non ci penso. Perché prendere il
Non si vede? Infatti no, se non faccio condividi schermo intero purtroppo non vedi adesso.
Però pure prima.
Vedi adesso che si vede? Non so perché fa queste cose.
Ora sì, però.
Lo si vede con la mia.
Ora non si vede con me. Abbiamo qualche minuto un problema con l'ansia.
Un minuto. Allora, perché? Allora io faccio così. Qui è solo questo, mentre questo è che pure in turco, capisci? Allora, se faccio schermo intero ho detto che non si vede, quindi se faccio così, vediamo se si vede.
Io ora vedo il fatto che serve fuori fase come tempo.
Ah, è fuori fase come tempo, sì, e si vede solo quello che...
Proviamo quella di prima, perché magari era fuori fase tutto, però magari funziona. Aspettiamo 30 secondi. No, sono solo quella
sì, era questo.
Già partito?
Sì.
In teoria ora devo però
Vedi se si vede questa, si vede vedere questa slide,
io vedo questo.
ok,
Però aspettiamo un attimo, perché secondo me
sì.
sta andando quella di lì ancora. Un po' di carte. Cosa sta strano? C'è qualcosa che insomma in questo momento non
Mi ricordo ieri, infatti poi non presente.
voglio solo che proprio non è messo. Se va avanti con il qualche slide, e questo non si muove, quindi non so cosa
È questa modalità, la modalità è solo per presentazione PowerPoint, sembra che non va.
Le altre modalità non ci sono.
L'altra modalità o è schermo intero dove si vedono le note, oppure bisogna andare online. No, non c'è possibilità. A meno che posso chiedere
Quindi hai detto che bisogna prima presentare e poi condividere lo schermo. Vai.
Presentare.
Sì.
Dopodiché andiamo di nuovo su qui e decidiamo di condividere PowerPoint slideshow.
Ok, grazie.
In realtà andare direttamente su.
La presentazione.
Okay, so let me activate the laser pointer. So thank you very much for your presentation, Mr. Chairman. So I'm here to present a work in cooperation with Martina Buzzetti and Natalia Pingaro, two of my PhD students, and the topic is the finite element upper bound limit analysis for the automatic identification of collapse mechanisms in mesory structures. So just a first slide, then to identify then the problem. The problem is the fact that historical buildings, especially in Europe, are very diffused. Here we can find the three examples in seismic areas. So we have Rome, Naples, and Athens. We have also Istanbul as well, but this is a slide, let's say, that we use many times. So I apologize then for having missed then Istanbul, but also in Turkey. Then we have several examples of historical buildings made by masonry that are highly vulnerable to seismic actions, so to horizontal loads. And one of the main straightforward strategies that we have then to evaluate the seismic vulnerability of such kind of structures is limit analysis. Limit analysis is very interesting because it's sufficiently simple, but is also powerful because goes beyond elasticity and therefore is able then to give information on the behavior of such kind of structures near the collapse. The hypotheses, as you probably already know, are very simple, and the solution can be found very quickly. One of the main problems is the fact that, for instance, the Italian code then uses limit analysis in the identification of the so-called triggering of partial failure mechanisms. So for the evaluation of the vulnerability of existing buildings, and historical buildings, of course, are an example of existing buildings. But the main drawback is the fact that the Italian code then suggests the user to identify at the beginning pre-assigned failure mechanisms. And the utilization of the kinematic approach then may lead to an overestimation of the load carrying capacity. In order to counterbalance, let's say, this drawback, the Italian code requires also that masonry is modeled as an attention material, and this within linear programming may represent a big problem. In the literature, and I have, with my research group, a long experience in this regard. There are examples where limit analysis is combined with finite elements. And this work presents then very concisely some of the main features of one of these finite element codes that we have called accolade. Accolade stands for the acceleration determination of at collapse of under horizontal loads for masonry buildings, so it's a sort of acronym, and is quite developed because it's very user-friendly. than in this version. We are at the 6th version at present, and basically discretized any kind of three-dimensional mesory structure by means of a discretization that is constituted by 3D infinitely resistant hexahedron elements that interact with four-noded interfaces. You have also the possibility to use other materials. For instance, here you see a concrete ring beam, then in this example. You see then rigid beams that can be also modeled with a certain strength. So in order to model also reinforced concrete beams and also wooden beams. We have also the possibility to insert the tie rods. We have the possibility then to model the measuring material with an heterogeneous approach, so with different blocks with their geometry, three-dimensional geometry, and this is particularly important, for instance, and it is well represented here when you want then to take into consideration that the interaction that you have in terms of resistance, of strength, between perpendicular walls, so the role played by the texture near the corner. And of course, then you can also model mesory as an homogeneous material, and we will see then in the next slide in which manner then we deal with the non-tension material problem. Regardless then the strength domain that you select for the interfaces, when you discretize in limit analysis any kind of three-dimensional structure and you use an upper bound approach, then the problem that you have to solve is automatized, and it relies into to find then the minimum of a certain function that represents the collapse multiplier. And this function is the difference between the power that is dissipated at the interfaces, that is this term, minus the power that is expended by the system of forces that are independent from the load multiplier. So the primary variables here are the velocities of the generalized velocities of the hexahedron elements, so rotation rates, and velocities, linear velocities of the centroid of the element, and the plastic multipliers at the interfaces. So this function that is linear, that is also called objective function, is subjected to a set of equality and inequality constraints. So the equality constraints basically are the compatibility of the velocities at the interfaces that involve the velocities of the elements and the plastic multipliers of the interfaces. Then there is a single equation that is a normalization equation that is useful in order then to select one failure mechanism among the infinite possible homothetic mechanisms that are associated to the same collapse multiplier. Then we have other equality constraints that represent the boundary conditions. If you have the presence of, for instance, tie rods, you have additional equality constraints, and then you have the non-negativity of the plastic multipliers at the interfaces. So it seems complex, but at the end of the day, then to solve such problem nowadays with a computer is a piece of cake. But now let's go to analyze in this slide the problem of the non-tension material. When you deal with a non-tension material, and this is required by the Italian code, so actually we can't circumvent such problem. The problem mathematically is that the algorithm of limit is tends to become very small. Here on the left, we have a possible strength domain for an interface. So it's a more Coulomb failure criterion, that is the blue, let's say, domain, with a tension cutoff and a compressive cutoff that represents in a reasonable manner, let's say, the behavior of the problem is that when this Ft, so the tensile strength, goes to zero, so the strength of main shrinks to zero, then the solution then is affected by premature halting. So in some cases then the solution is not found, or in other cases then you have a spurious sliding in the solution. That is something that is undesired, and also is something that is in disagreement with what stated by with what required by the Italian code and what stated, for instance, by Heimann. So the idea that we presented to deal with, to circumvent such numerical problems that are purely numerical is an idea that is pretty simple conceptually. It was published by me and one of my PhDs was to shrink then the failure surface progressively to zero. So to pass from, so to repeat iteratively some linear programming computations with the same shape of failure surface, but shrinking progressively the failure solutions. So the blue one and the orange one, that the failure mechanism doesn't change. So thanks to the normalization conditions, so the distribution of the horizon of the field of velocities of the elements is the same. So this means that the external power that is dissipated, that is expended, is the same, and the power expended at the interfaces, so dissipated at the interfaces, drops down linearly. So when you see that the trend of the collapse multiplier then progressively with Ft decreases linearly, this means that the failure surface doesn't change, the failure mechanism doesn't change. Progressively, then, when you reduce too much Ft, then the trend of the collapse multiplier then becomes different from the linearity. So the collapse multiplier drops down in a nonlinear way, and this means that spurious sliding is occurring. So with an extrapolation, then when you are able then to identify a failure mechanism that is not affected by spurious sliding, so with a simple linear extrapolation, then you can find the collapse multiplier that is associated to the hypothesis of the no-tension material. And this is something that is particularly interesting because, as I mentioned before, the Italian code, so the technical code on the constructions, the very recent one that dates back to 2018, that requires then to evaluate this acceleration, let's say, parameter that is called A0 star. A0 star is equal to the ratio between the collapse multiplier, that is called in the Italian code alpha 0, multiplied by the gravity acceleration and divided by a confidence factor. A confidence factor, let's say, is a number, and again by another parameter that is called E star. E star is the fraction of the participating mass that is provided by this formula. This formula contains at the numerator m star. M star depends on is the classic participating mass. The participating mass in this case, since we are within limit analysis, depends on the horizontal velocities of the hexaedron elements, and P and Pi represent then the self-weight of the hexaedron element. So according to this formula, then you are able to evaluate m star. With m star, you are able to evaluate E star, and with E star, you are able to evaluate A0 star. There is a problem with m star because it depends on the velocity, on the horizontal velocities of the elements. And very recently, then with Martina and Natalia, so the two co-authors of this work, then we proposed then a filter on the velocities to consider only the elements that are involved in the mechanisms. So on the right, then you can see an example is a is a prototype that was tested some years ago on a shaking table in Lisbon, and we have here a comparison between the failure mechanism found with limit analysis and those found experimentally. So the match is quite comfortable, and then you can see that progressively, then if you increase then the percentage of the elements that are involved in the failure, are considered involved in the failure mechanism, so with the horizontal velocity that is considered relevant, so in terms of percentage, here you can find three hypotheses, A, B, C, depending if then the elements that failure mechanism are considered the 10% of the maximum velocity or the 30% of the maximum elements that are have a color, a red color. So the orange ones are disregarded, but you can see that the trend then of the A0 star then decreases, but asymptotically. So we found that if you apply a filter equal to 20%, 15%, okay, the algorithm, so the answers then progressively works in a correct manner. So just to conclude, why it is important A0 star? It is important because the structure is verified, so it's safe if this A0 star is greater or equal to AG, that is the peak acceleration at the bedrock, it depends on the spectrum, multiplied again by another parameter S, that is the soil and topographic coefficient, over the behavior factor, that is a number, generally for measuring for partial failure mechanism, it is 1. So let's go and to see an example. A portion della patient is located in Piacenza, is the most interesting part, the one in green, that you can see on the left, because then the geometry of this portion is very complex and very irregular. We have a cloister vault with a big span at the ground floor that is surrounded at the keystone by a quite heavy wall, that is this one. Okay, and so we have stability problems of the vault, but then this portion is also, as intuitively pretty obvious, is also very vulnerable to seismic loads, so to horizontal accelerations. Also because at the first floor is very tall in this one, and is covered by cross vaults. So we have a big mass also in this position. This is the spectrum, the elastic spectrum, the different limit states, and the parameter that we have to take into consideration, that we have already commented in the previous slide, so is Ag multiplied by S over Q, is equal in this case to 0.68 meters over second square. So it's a number that we have to compare with the results obtained with limit analysis. And here are the results. So we applied two load distributions, again according to the Italian code, so inverse linear, that is called G1, and constant, that is called G2. So along the two different directions, so perpendicular to the facade of this portion, so along this direction, so from the north to the south, from the south to the north, okay, this direction. And so transversally, then from let's say the left to the right, and transversally from the right to the left. This one is the failure mechanism with a certain filter that is equal to 10% in case of a distribution that is equal to G1, and this one is the situation, so the response for the G2 distribution. As you can see, then for the G1 distribution, then the results then of limit analysis tell us that for the non-tension material hypothesis that is obtained with the procedure, with the iterative procedure that we have discussed in the previous slide, then the structure is not verified. So this means that, but it is something that is quite frequent, that the G1 distribution is the distribution that could be considered the worst loading condition. So what to do when we, with limit analysis, then, so the most straightforward way, technical way to decrease the vulnerability is to place tie rods. So Accolade allows us then to place the tie rods that we desire, and let's see then the response of the structure. Then if we place at the near the roof for 4 tie rods, and then we strengthen also the cloister vault at the ground floor with other 3 tie rods. Let's see the response of the structure strengthened with this traditional system of strengthening, with subjected to a G1 distribution of horizontal accelerations. So here you can find the results in terms of collapse load, so with the extrapolation for the non-tension material, both for the direction y plus, this is the result, and y minus. And you can see that the results that you can find that increase the collapse multiplier, so increase the A0 star parameter, but still it is not enough. It is not enough because then this portion is very problematic even from a static point of view. So we have to think then in the future, then if we think about the technical problem, what to do in order then to decrease further the vulnerability. So just to conclude, because I am already on delay, then the advantages of the approach that combines upper bound limit analysis with finite element discretization, I think are pretty obvious. So we avoid then to hypothesize from the beginning a pre-assigned failure mechanism, and this is a great advantage. We can take into consideration also the case of the non-tension material that within linear programming is not an easy task. And also we can also evaluate then the effect of the introduction of a strengthening intervention, like for instance, a placement of tie rods in a certain position and in a certain number. Future developments are to couple, again, Accolade with a meta-heuristic approach that is based on a genetic algorithm, and we are developing then this approach in order to automatically let the computer then identify then the optimal placement of a strengthening intervention in order to increase in the most effective way then the load carrying capacity under the application of a certain distribution of horizontal loads. That's it. Thank you very much for your attention. If you have some questions or curiosities, I will be happy to discuss with you.
Thanks for your very clear and extremely interesting presentation. Any question from you? No? I have a couple of questions, but maybe more curiosity. The first one, when you talk, it's obviously a kinematic approach, but when there are these flow multipliers over the interfaces that you are considering the objective function, these multipliers, the kind of classic multipliers, are there kind of relative displacements in the three directions, no?
Yes, yes, they are connected. There is yes, the compatibility then tells
Okay.
you that the jump of velocities is equal to the plastic multiplier multiplied by the gradient of the strand domain.
When this is when you see that there is to avoid the sliding, it means that you are forcing the multiplier to have only hinging rather than.
Yes,
Okay. That's
flexural plastic hinges, yes, or this is not possible in any case. Then in that paper that we published 2 years ago by Wang and me, that Wang patient was my former PhD student, but we also tested then classic benchmarks of limit analysis with an attention material, then the approach is perfect with classic benchmarks, like for instance, if you have the arch or the portal, etc., classic benchmarks, where you have that the failure is triggered by the presence of flexural hinges, so according to the Hyman's approach. But in real cases, so when you have complex three-dimensional structures, then in some cases, there are some cases where you have sliding, but this sliding doesn't, let's say, dominate then the total amount of the power that is dissipated at the interfaces.
This is interesting because I was wondering for the 3D application that you also showed very nice in the research, the potential no.
Yeah, there is.
How much this can affect?
Yeah. There is also in that paper. Then there is case by case. Then there is a computation case by case of the portion of the power that is expended by, let's say, sliding,
Okay.
and the portion that is expended by flexural hinges.
So-
Then to see that there is a certain amount of power that is dissipated for sliding, but this is when compared with that is expended by normal stresses, this is negligible, let's say, or doesn't exceed, let's say, 5%. So we can say reasonably that we are within the hypothesis of Hyman, but then the final aim is that we are within the hypothesis of the Italian code. Because the Italian code for the triggering of the partial failure mechanism requires that then you use the hypothesis of Hyman.
Okay. The last one, but this is very good. When you shrink the domain, this means that you are going to solve sequential linear programming problems.
Yes,
Okay.
exactly. Yes, exactly. It's implemented exactly like this. Yeah, correct. Yeah.
Okay. Thank you, Prof. Thank you so much.
Thank you
for
to
the
you
presentation.
for the questions.
You need to do the same thing.
Facciamo io.
Farà solo qualcosa.
It should be here.
I'm going to present this work, which was made by. Essentially, this is the summary of a master thesis of this guy, Giuseppe Materazza, who graduated 3 months ago, and this was made together with Titti Cusano, the architect Ferrero, and the professor Maddaloni. So the title is Insight into okay. This is the index of the presentation. guide of the presentation. So, just to directly dive into the topic, this is a masonry bridge that was built kind of 150 years ago, next to Benevento. Benevento has this long-lasting history. I'll show you a couple of them. And well, the image, and we were able to find out that. So this collapsed, and we don't know the master students to interview local people in order to gather information. Well, at the end, we did also statistics about the information we received, because there is that it was built the first time, and it was there was an explosion during the Second World War caused by the retreat of the Nazi army, and it was after that was rebuilt, and then it collapsed. The last time it was during the 60s of the previous century. So this is the only information we knew. We were not able to find any other documentation on the bridge. So essentially, this bridge was connecting these two straight. This is what we can see from Google Map. This is the remaining of the bridge. And the old street was passing to the valley this way. You know, I need to use this way. Well, just to, I'll go briefly to the introduction with the mechanics of this bridge. It's mostly ruled by the mechanics of the arches, which were used from in the past centuries to build aqueduct bridges and to were helpful to the broader Roman civilization. This is one of the most ancient masonry bridges you can find in Benevento. This was built by the Roma during the second century before Christ by the Roman. Is still in use. So, and there are many like this that are still present in the area. The mechanics of the masonry structures are also in the previous presentation. Professor Milani said it's very complicated because of the geometry goes into the equilibrium, the mechanics, the vulnerability with respect to horizontal actions, so they are susceptible to horizontal actions. But essentially, the geometry is ruled by the shape. The equilibrium is ruled by the shape of these structures. We know very well that there is a naive use of standard finite element method is not the best way to solve these mechanical problems. If you apply this standard FE application to an example, this is the Segovia aqueduct geometry, they will tell you that the structure is not standing even for gravitational load, and we know very well that this is not like this because it stands. And if you apply kind of very simple equilibrium, like limit analysis equilibrium formulation thematic approach, you can easily calculate that this is stable and how much this is stable. Essentially, we know that what we have tried to do with this topic is to use the 3D elements software with this master student, trying to apply kind of to reframe the 3D within the IMNI assumptions, which are the not we know very well that measure has not inside strength, infinite compressive capacity, and there's no sliding to the collapse. So, which for us, who work in masonry continuum mechanics, this assumption can be translated this way. What we ruled off from the tree that we know that sliding is possible, we will try to deal with sliding with the sliding coefficient that were set up to 35 degrees. So, tree deck, I'm not going to spend time on tree deck when this, I think this one we know extremely well. Tree deck, a distinct element method can be defined as them solve if these three assumptions apply. And essentially, you can model blocks as rigid or deformable. You can also provide internal interfaces where you can provide a non-negligible tensile capacity for the contact, which are mainly ruled by normal tangential stiffness. But somehow, this normal tangential stiffness, even though this is, in my opinion, there are a lot of papers that deal with how to calculate these values. Essentially, if you, as De Jong demonstrated a few years ago, if you consider these values divided by 2 order, 3 order, 4 order less, the solution in terms of capacity or load bearing capacity or displacement capacity does not change that much. While the computational time changes and reduces a lot. So this is essentially the constitutive model you may select using a 3-deck. When you have two subcontacts like A, B, you can define a normal and tangential stiffness, where can also provide with cohesion if you want to model some tensile capacity. What we did with these two students and applied with this one, we worked in a kind of, we defined a Python pipeline to work in Rhino while defining parametric geometries and importing this geometry in 3-deck, using 3-deck in the ground as much as possible to be back in Rhino to visualize the results. More or less, this is what we did in order to deal more easily with 3-deck or with the fish code that is used by 3-deck, which is not in the version 5.6.7, is not super easy to deal with. This is an example. Well, this is a code that we worked with a student in Python to export geometries that then were used in 3-deck and so on. This is a typical screen that you may see in 3-deck, where you can generate this code easily and then run all your kind of analysis in order to perform displacement or bending capacity analysis and also assign material properties in an easy way. Well, here you cannot, well, it's not readable. This was a screenshot of the Python code we used to post-process the results. And with the master student, it was totally new to measuring mechanics. And we started from the kind of calibration analysis in order to understand which are the best parameters we can use to simulate displacement capacity analysis, and also to investigate the role of the geometry. So it started, first he was curious about what is the difference in terms of capacity, load bearing, and displacement capacity if we consider the perfect semicircular geometry or other than something that is linearized, like something happen like this. We did a lot of analysis, indeed, parametric investigations. At the end, we know that if from computational point of view, if you go for something that is linear, that's okay, but sometimes you need more time also for the calculation. So because in any case you need to discretize the block with many points. So what we did is in any case to analyze both geometries, and in this case to perform a parametric analysis in order to investigate which was the ideal ratio among segment velocity and internal radius to get good result in let's say in acceptable computational time. And in this case, it was the radius was 1 meter, and it's 1% technically the displacement step we need to apply to get something that is closer. This was also benchmarked against we did different parametric analysis for this test. Just to go back to the problem, to our problem. This is a joke that this part of the bridge, what we will see in the next slide as right abutment, is technically subjected to a landslide. This is the point out that we did with both local architects. And south and north parallel. We are gonna analyze only the 2D geometry of the south parallel. This is a zoom in on the stereotomy. You may see that this is another issue we had, was that there was a lot of vegetation, and it was for us technically impossible to understand correctly the boundary of the structure. This is the craft pattern that tells us that more or less there is a clockwise rotation maybe right after the collapse. The stereotomy is quite regular, essentially. The course is horizontal, essentially was very regular. This was the portion of the bridge that was built in the 1860s. To gather more information, we were maybe lucky that a person told us that there was a twin bridge next to this, and the twin bridge technically is this one still in use. As you may appreciate in this twin bridge, the first thing we noticed, this slide doesn't work, okay, is first there are a lot of similarities between this twin bridge and the other one that collapsed. But the other thing, which is in my opinion truly important, is this. If you zoom in, I think that should be then the next slide. No. Here on the bottom. This is a concrete reinforced arch placed over the masonry arch, probably right after the 60s of the previous century. The reason one of the motivation about the displacement was that probably, most likely, as we will see at the end of this analysis, the thickness of the masonry arch is not enough to stand on its own weight. Or better, it's very close to the minimum thickness. This is the geometry that we reconstructed. Also, we made some assumption on the right part of the bridge that collapsed, and we were able to gather information from the foundation of the right part where there were still traces of the old abutment. And this is the geometry stereotomy that we are gonna use. The internal radius is something higher than 8 meters. The first analysis we did, it took was a displacement capacity analysis of the right pillar. The first analysis with a random displacement, just to understand the computation time, it took, with also the reduced value of the stiffness and so on, it took more than 1 day, normal after. So we decided to analyze a smaller part of the structure, like this, and with this kind of boundary condition. You can see the red blocks are kind of supports, and on the right we apply displacement condition. This is essentially the layer we consider in the analysis. We are consider the green layer, the green blocks were assigned the highest value of the normal tangential thickness, while the other were reduced because of the infill that is in between the two bridge paraments, considered the Young equation. And this was the first analysis we did with these boundary conditions. So there were numerical problems from the very beginning here, because the blocks as they are reached were over-constrained on the left part. And so we decided to change that. Here an overview of what happened at the first step of the analysis. And so we decided to remove the boundary condition on the left to place an additional load that was simulating the pressure, the rest lateral pressure of the earth, which was calculating according to this equation. It was implemented in 3DEC and we were able to track the interfaces and to apply in each step this pressure in order to keep the action of the earth in account. So what we did essentially was a parametric analysis, consider different inclination of the foundation segment, like this, 40, 50, 30, 35 degrees till the collapse. And here on the left, upper left, you may see this is the collapse displacement. And what we were able to understand it was that essentially the solution based on the information that we gather on the foundation of the right path, by the final the formal configuration of the bridge, the solution in terms of displacement should have been around 1 meter. So what we were able to understand is that almost likely the foundation displacement that caused the collapse was around 20-25 degrees. And what is important is that even now, considering all this upper structure of the parament that is collaborating with the arch as a resisting structure, the collapse displacement is around 1 meter. 1 meter is 1/8 of the internal radius, which is not that high for a major arch because there can exhibit some non-negligible ductility under displacement. And the reason was that if you essentially, if you remove the parament, this arch without the parament, because of this spinning angle that makes this arch kind of semicircular, is very close to the minimum thickness. Should avoid, be avoided, no? And this explains also why in the other, maybe in the other bridge, the twin bridge, they were able to keep it alive, designing this repulsive concrete structure. So this is a video of the collapse mechanism. And when we went back at the end to compare what is this remaining part here, we have this kind of comparison among the 3D model and what is the remaining structure of the bridge. The upper part was not considered because it's a very thin parament that was not considered in the analysis. So essentially, this is kind of a first analysis we did. It required, to be honest, a lot of effort from the geometrical modeling perspective. The idea is with also this thought that try to restore this bridge to do something in order to keep back alive. I'm done with the presentation, so thank you for that.
I have a question for you. So congratulations for the case study. It's extremely to know that you are involved in that is a big problem. It's very tricky to deal with the foundation step and some other structures. But you mentioned that you use feedback, very interesting simulations, etc. But then you limit the analysis only to the central portion. But since so I saw that you used many blocks, but of course the text is different from the real one. Would it be better than to use the biggest block and maintaining the proportion of the blocks, bigger blocks? But
what we did, yeah. Technically, I didn't say this, but we did it. So we used the ratio of this ideal block we use in the analysis. It contains 4 real blocks, and we tried different solutions with something even bigger, but the results were not so accurate. So we decided to go for this because otherwise we should have considered an extremely high number of blocks. And this was. It took the analysis of the small bridge takes usually one displacement capacity analysis from 4 to 5 hours. It's quite a lot. It's quite a lot.
Yeah.
Because
another option is that is still in action analysis. So I imagine that it's not very that why you use feedback.
Because we don't have the license, so. Well, we have the and at the beginning the idea was to start to do something with open supervisor. Essentially, to be honest, not my work. It's the work I supervise a student. And for me, it was super important for the student to let him acquire notions on a real problem directly, because otherwise he should have studied Python and not. So this was the compromise. And to be honest, well, maybe the next thing we can do is to start comparing this with some limit analysis solutions. Yeah. Oh, thank you. Oh.
I just didn't understand what was the relation between Rhino and Trinidad, how to connect to
No, we did with this a few Python scripts to export things from Rhino, to import in 3DEC, to export results from 3DEC, to rebuild results in Rhino just to analyze and visualize things differently. And also, to be honest, I didn't show this in this presentation because it was not part of this work. Also in internal forces, an example. Also internal forces. And we did but we did this with and we applied this with another guy who graduated a month ago. And this is the slide I showed you before. Few seconds. Sorry. Okay. So this one is the geometry rebuilt with internal forces from 3. From 3. So this is, and they are, if you look, they are very goes to the inches as they should be. These are the resultant calculated because from 3 that you get back subconduct forces. Then you have to repeat the resultant over the interface, but it looks like limit analysis, but it's not limit analysis, it's 3D. But in the case of the beach, so in the end, yes, sometimes somehow they can have, but in the case of the beach, we didn't find any.
So this internal forces that you found is something that physics found, right?
Yes. We didn't do so. The only thing we did was just to post-process the results.
And how do you do that?
In fish.
Oh, with just a fish, but how?
Fish.
Fish, how is the post-processing?
No. You have to code in fish. You have to code to extract values and to rebuild values. It's not easy, to be honest.
No, I meant that at internet we try to find the surfaces and then we try to sum them up.
Yes, exactly.
And tangential or also both tangential and normal?
As you want. Ideally, you can go either way. Yeah. And then, so the next presenter is so the next presentation is by Natalia Pingaro. The title of the presentation is Fermanola, version 3.0 as a tool to predict settlement-induced cracks in masonry walls. Just a second.
Okay, so thank you for the introduction. I am Natalia Pingaro, a PhD student from Politecnico di Milano, and I am here to present a work done in collaboration with my supervisor, Professor Gabriele Milani, which is titled Fermanola as a tool to predict the settlement-induced cracks in masonry walls. Let us see the outline of the presentation. Basically, we will start with an introduction regarding the motivation behind such a research. then the research work, which is subdivided in explaining you the theoretical background of Femanola, homemade code, and then this code will be validated using a benchmark available in the literature and related to a measuring wall subjected to soil settlement, for which both experimental and numerical results are available. And finally, I will draw some conclusions with the advantages of the procedure and possible future developments of the work. I have to apologize for the same pictures, but unfortunately this is a common slide in our research group, but the content are different, and the stability of measuring structures is nowadays an open problem, and the importance of the investigation is straightforward and clear because these structures constitute a significant portion of the architectural heritage, and diffused all over the world are collapses for the application of direct and indirect seismic excitation and for vertical loads and soil settlement in historical measuring structures. For these reasons, the analysis beyond the elastic limit are subjected to countless studies aimed at a sound consolidation, and nowadays there are no sufficiently simple and predictive computational models able to provide information on the actual and future vulnerabilities, and therefore the proposal of simple models to put at disposal to designer is a computational priority. With such a need in mind, let's see now our proposal. Femanola, which stands for Finite Element Measuring Nonlinear Analysis, is a new developed in-house nonlinear static finite element software which employs a fully explicit iterative elastic method to handle material nonlinearities. The mortar joints are discretized using 4-node isoparametric elements with the normal stiffness in the joint direction set to 0. The joints can be either meshed with their real thickness or with a negligible one in order to simulate, for example, dry joints or interfaces as in a standard heterogeneous discretization. The problem is based on plane stress assumptions, though plane strain problems can also be addressed. The element stiffness matrix is written in a standard form, where D represents the elastic stiffness of the joint, J is the Jacobian of the transformation from physical to natural coordinates, while B is the matrix of the first derivatives of the shape function, and finally a rotation R is applied to transform the element stiffness matrix into the global coordinate system. As far as the nonlinear behavior is concerned, its general features are reported here in the two charts in the bottom part of the slide, where it is possible to notice the penalization strategy used for elastic and shear modules at a Gauss point experiencing softening in shear, so left, and tension, right. It is interesting to let you know that the parameters needed to set the input by the user can be simply inserted in a user-friendly Excel spreadsheet, which is directly connected to the MATLAB nonlinear finite element software, as it is possible to see here in the slide. So basically, let us start with the tensile behavior of the joints, which is defined with a linear exponential softening behavior. In particular, the elastic phase is defined by the elastic modulus and by the peak tensile strength, whereas the exponential softening branch is defined by a certain fracture energy which works in mode 1. The formulas employed to calibrate the tensile behavior are those reported here in the slide. In contrast to the tensile behavior, the compressive behavior is characterized by discrete data points in order to reproduce the typical hardening softening behavior which can be observed in a joint subjected to compression. In this case, the parameters used to set the elastic phase of this compressive behavior are the peak compressive strength and the same elastic modulus obviously used to define the tensile behavior. Finally, the tangential behavior is defined by a linear exponential relationship between shear strain and shear stresses, which is influenced by the normal stresses acting across the interface. This relationship follows a cohesive frictional law. In this case, the parameters used are the following. So basically the peak tangential strength and the residual one, the friction angle, the shear modulus, and a certain fracture energy, which in this case works in mode 2, and a non-dimensional parameter C, which follows a parabolic trend, as it is possible to see in the chart reported in the right part of the slide. As I have anticipated you, this code is validated using a benchmark available in the literature related to a measuring wall subjected to soil settlements, for which both numerical and experimental results are available. In particular, the numerical approach available refers to a limit analysis-based method proposed by Tiberti and co-workers, and the experimental paper was done by Napolitano and Glisic. The geometrical features of this wall are reported here in the slide. So let us start with the global behavior found within Femanola. And before, I would like to tell you that in node 771, 733, 783, 735, and 212 are those where the unit displacements are applied. And if you notice the chart, it is interesting to notice that the reaction forces found for node 771, 783, and 212 are close to zero and overlap almost at the origin, if you can notice in the chart. This is not surprising because if you notice, the most significant reaction forces are those found for node 733 and 735, almost in correspondence of the centroid of the two blocks. And additionally, the reaction force found at node 735 is larger than that at node 733. This is because the two forces are the displacement constant and to basically avoid rotation. Let us see now the localized behavior found within Femanola context, plotted for steps 13 and 50 of 50, and related to the tangential stresses and the state of shear damage. And for normal stresses and state of tensile damage. Interesting to notice that at the beginning of the analysis, so basically at step 13, the damage is localized close to the application of the unit displacements, whereas at the end of the analysis, it is possible to notice the typical arcuate detachment that can be observed in a measuring wall subjected to soil settlement, features that was also observed by Tiberti et al. Within limit analysis approach and experimentally by Napolitano and Glisic. Then I would like to show you also a zoom related to the state of tensile damage, where it is possible to notice clearly the hinge opening, and another zoom in correspondence of the application of the unit displacement, where the failure mechanism almost overlap the experimental finding. So to conclude this presentation, presented you Femanola, which stands for Finite Element Measuring or Linear Analysis, which is a new software implemented in order to simulate the failure of the structures under both mode 1 and 2, and give us the ability to analyze different benchmarks. Here I present only one, which is referred to a masonry wall subjected to soil settlement, but we are working on masonry arches, masonry triplet test, and other benchmarks. Among the advantages of the procedure, we can for sure say that this approach gives us the possibility to use low-cost software. It is characterized by a robust algorithm, even if compared with more sophisticated approaches. It can be used in common design by an experienced user because basically the user needs only the Excel spreadsheet that I have shown you just a few minutes ago. And we are working on implementing Femanola in a 3D environment. So that's it. Thank you so much for your attention, and I'm here to reply to your questions, if any.
Thank you for the presentation. Super, very interesting. Any question?
I just have like a very quick question about it. The geometry that you showed was running one pattern and the stacked one pattern. It's a clear that they are stacked, right? So,
This one.
this is the running one.
Yeah,
Okay.
exactly.
And then with the rest.
Because here is a mesh discretization. So basically, yes, exactly. Running blocks in the mesh. Then sometimes we have a joint, which is modeled within the theoretical framework that I have explained to you, and sometimes it is only characterized by two four-noded elements.
Very simple. But these colors that we see on the interfaces are exactly the distribution of the stresses over the interface.
Yeah, exactly.
And when you say you write the load step 13, it's because you say load step because you are applying it.
Because I can choose how many steps I want in the analysis.
No, the word the load. Even if you are applying.
Sorry, here.
No, but after.
Okay.
Example, load step.
Okay. Yeah. Okay.
This is because you are applying this displacement forces.
Yeah, exactly.
Okay,
Yeah. Sorry, I didn't get your question.
Okay. Okay. That was the. And do you have any kind of diagram of displacement versus value of these forces?
Yeah, we have, but I don't have here in the
because I was
I can show
shape
you
of the
maybe later if you want.
So it's very. How long does it take?
3 minutes.
3 minutes also.
Yeah.
Okay.
Maybe less. Depends on the
And this is
benchmark.
sequential.
Yeah.
How many steps? 15. So
50 in this case.
So 3 minutes 50 steps.
Yeah.
Which is very good.
But I ran recently an analysis related to a masonry arch where I decided to increase the number of steps to 200, but the time was like 5 minutes, 6 minutes. So yeah, very
fast.
reasonable from a computational point of view.
Compared to okay, thank you.
Thank you.
So the first session ends here, and then we will take a break and we'll start soon.
La cosa es que también supuestamente es el que, según, o sea, al menos el profesor hablando de la cosa es el proceso. Es cierto que no es interesante, ya me quiere, ya no sí, claro, podría ser más, también podría ser tradiciones. Sí, pero la cosa es que nadie quiere la ya no es más. Marca no puede ser. O sea, marca no puede ser. Claro, claro. Sí, podría ser. O sea, proponer podría ser, pero la cuestión es que basta que contra el gato y no la todavía muerto, pero es que no puede ser mal, no, pero da igual como la actriz sea, o sea, si aquí no es lo que vea, pero bueno, eso lo que decir. Entonces, o Xavi es el marco responsable, o Miguel de Altido se debe que mandar sí. Pero seguro ¿qué pasa? Continúa. Come va?
Bene.
Bene.
Ho messo il nome che uso sempre, però non me lo fa cambiare.
Forse dovreste uscire, forse
Devo uscire?
Quando
Adesso?
si rientra fa rimettere il nome.
Ah, ok, mo riesco.
Ok.
Avevo paura che mi faceva uscire e non mi faceva rientrare mai più.
No, è perché l'ho fatto ieri sera, l'ho fatto prima, l'ho fatto adesso per provare.
Andrea, fammi un favore.
Che ne?
Vedi un po'. Tu vedi la presentazione?
Sì.
Ok, d'accordo. Posso lasciarla, tanto solo la prima.
Sì, penso di sì, direi di sì.
Siamo noi e te.
No, siamo 4, mi pare.
No, il 4 è un fellow.
No,
Gypsy
dico
fellow.
nel calendario, dico
Ah, sì.
nella sessione.
No, pensavo 4 adesso, ma 4 adesso
No,
no.
diciamo nella sessione siamo... Poi c'è la prima, poi ci sta Luciana dopo.
Poi c'è Luciana c'è, sicuramente, mo
Poi ci
arriva.
sono io e poi l'ultimo non mi ricordo, l'ultimo è Carlo.
Poi ci
Comunque
sei tu che
siamo...
presenti e poi c'è Sam Cooking.
o Carlo, non lo so chi è che presenta.
Ma mi sa che Carlo sta
No, Carlo non è andato là.
in altre faccende, affaccendato.
Ah, che ne sa, vabbè.
Beato lui, guarda. Andrea, non
Non
ti
so,
preoccupare, che fra poco ti capita pure a te.
non so
Anzi,
quali sono le faccende sue. Comunque.
congratulazioni.
Vabbè.
Per fortuna mi sono ricordata che c'è l'ora di differenza, perché se no io
Pure io ci ho
aspettavo,
pensato ieri. Sì.
ci sono cascata, guarda.
No, ci ho pensato io quando ho visto il coso e sono andato a leggere sopra.
Ma se non avessi fatto ieri un collegamento con Antonino, non ci avrei mai pensato.
Mm.
No. Antonino sta libero.
Sì, ma l'ho visto perché mi sono collegato un attimo alla cosa di prima. Ho ascoltato, ma no, mi sono collegato prima, ho sentito un po' quella sessione di prima, ho sentito Milano, ho sentito Antonino, ho sentito questa ragazza.
Ah. Le aprono con le chiavi, le room virtuali,
Ma che ne so.
con le chiavi di metallo.
Se non vuoi dire Arduino, che fine fa?
Ma
Pronto? No, ci vediamo io e siamo io e la Monaco collegati. Sì, qui siamo qua. Ciao.
adesso mando un messaggio a...
No, mi ha chiamato Mo, dice che hanno un problema di connessione. No,
Oh, vabbè.
a muoversi da qua.
No, stavo mandando un messaggio a Luciana.
Ah, a Luciano, sì.
No, glielo mando a Luciana Di Gennaro.
Sì, no, Mo diceva Antonino mi ha chiamato lui a me, ma.
Mi posso allontanare un minuto, Andrea? Tanto io ci sono...
Per me sì, se non troppo.
No, ci sono un minuto solo, tanto arrivo subito. Vado a prendere un bicchiere d'acqua. Sposto.
Dimmi. Poi.
Una cosa, scrivi nella chat in modo che poi tutti lo vedano. La
Eh.
lezione inizierà fra qualche minuto.
Sì, ma in questo momento siamo solo io e la Monaco, perché cosa né Luciana né...
Non capisci.
A che ora?
Scrive, noi non possiamo scrivere.
Ok.
16 e 15.
Ah, 16 e 15.
No, ci sono.
Ok.
Ma quanti sono in stanza, in aula? Ci sta solo Antonino?
No, non lo so, ma mi ha chiamato perché c'è qualche problema, mi ha chiesto di scrivere il messaggio che mi ha messo. Ma Luciano manca si è collegato però.
Mo gli ho mandato il messaggio.
Ah, ma io tutte e due stanno tutte e due in coglioni col fuso orario?
Non se lo ricordava.
Non lo so, sto chiedendo, ma lo dico pure a Carlo.
Sta arrivando anche Luciana,
Ok.
Siamo a posto. La sessione è chiusa, chi manca?
Mancano Luciana e Semmo, Carlo. Chi è?
Ma Carlo che ha detto?
Ma gli ho scritto a Carlo.
Questo sistema è bello però, sai?
Questo dei Giazzi, questa piattaforma
Giz,
diciamo.
sì.
Sì, boh, sì, come...
E come Meet, è un po' più duttile sui tempi perché è gratuito, è un'ora.
Ah.
Ah.
No,
Quindi
boh,
secondo me
questa è pubblica,
più...
non è sviluppata, cioè non è roba loro.
Eh?
È pubblica, non è roba loro, di questi della conferenza.
No, ma penso che abbiano pagato per questa conferenza per ottenere collegamenti più lunghi.
Ok.
Perché è gratuito fino a 60 minuti.
No, io non
Almeno
lo
così.
conoscevo. Non lo conoscevo, vedo che funziona bene, però non lo
No, io
conoscevo.
neanche, però poi mi sono informata per capire se era una cosa, diciamo, statale, per esempio, oppure una company autonoma.
Ma mi si sente bene?
No, a me mi pare comodo, è semplice.
No, dico a me mi si sente bene perché oggi qualcuno mi lamentava problemi di
A te ti si
connessione.
sente bene, dovresti alzare un po' il microfono perché ti sento basso.
Prova.
Adesso
No, io
un po'.
mi sento benissimo. No, me lo sono attaccato sul bottone.
Ah, vabbè. No, il
Però
microfono di questo computer è buono.
No, vabbè, io sto con le cuffiette perché mi dà fastidio il rumore di fondo. Preferisco stare più isolato.
Da noi fa talmente caldo.
Ma pure qua, stai scherzando, io non me lo ricordavo gli altri anni così caldo.
Vabbè, ma quando finisce questa cosa io me ne vado a Vallata, sto al fresco. Ieri stavo con la copertina.
Ma voi sapete, ma non so se abbiamo tempo di parlare, però io conosco in realtà uno che è stato prete a Vallata per un po' di tempo e che mo sta proprio a Istanbul come vescovo. Si chiama Massimiliano Palinuro.
Ma Palinuro non è un cognome nostro.
No, era lui è di Ariano, credo. Però ha fatto il parroco a Vallata, se non ricordo male.
Ah, Don Massimiliano, sì.
Don Massimiliano Palinuro. O a Vallata o a San Nicola Baronia, non mi ricordo. E adesso...
Noi teniamo un prete che è una pessima persona.
No, non li conosco.
Non voglio parlare male di nessuno.
Io conosco solo questo qua perché era amico del prete che sta a Salerno. E adesso questo qui è vescovo a Istanbul proprio. È stato per molti anni missionario in Turchia, in altre parti, e ora è diventato vescovo a Istanbul. Pensavo che essendo di Vallata lo conosceva.
No, perché noi teniamo a prestito il prete di Carife, che da Carife hanno cacciato perché non era una gran persona.
No, non li conosco.
E quindi mo si è venuto a Vallata e sta facendo le stesse cose, diciamo, che faceva all'epoca.
No, non li conosco.
Ma ci fanno collegare?
Che ne sai, noi stiamo collegati, no? Mi informo, reitero la richiesta di...
Scusate, io non vi ho salutato.
Buongiorno.
Lucia, entra ed esci e metti il nome.
Ah, è scritto me. Ok.
Cioè no, esci ed entra. No, entra ed esci. Maronna, mia, sto esaurita, fa troppo caldo.
Va bene, a tra poco.
Sì. Ecco ricordo chi era questo fellow Gister.
No, ma ce ne sta pure un altro sotto.
Non so chi è. Vedi che mo si vede Luciana Di Gennaro?
Un po' meglio di me.
Sì. È meglio di fellow Gister là, Gister. Come si dice?
Beh, perché questa piattaforma si chiama Jitsi, quindi era Jitser.
Gister.
Ah.
Però mentre su quello sullo stemma c'è la T prima della S, qua invece hanno scritto la S prima della T. Non so se va bene così o no.
Ma no, non so fatto caso. E penso che... No, c'è la T prima e dopo. C'è la T prima e la T dopo. Git terra.
TS.
TST.
Jitsi Meet. Jitsi Meet. Jitsi prima la T e poi la S.
Un attimo Alessandra, che sta là, magari però senza stare impicciata con...
Ma... Un quarto d'ora di ritardo. Si è giocato tutto il mio tempo. Adesso io mi collego, dico guardate, questo è il titolo della mia presentazione, io avrei finito. Grazie.
Con loro, vabbè, io chiamalo te pensando che... Che stessi nei paraggi senza essere impicciata.
Ma mi spiccio, la faccio in poco tempo, guarda, perché proprio non ne posso più.
Vabbè, niente. Certo. No, provo a chiamare Alessandra sperando che fosse nei paraggi, ma sarà un'altra parte. Che mi ha confermato che...
Lucia, scusa se ti ho fatto venire, ma pensavo che si spicciassero di più.
No, Michela, se non me lo dicevi io mi collegavo alle 4. Cioè, anzi, grazie, perché mi sono proprio... Questa cosa del fuso non l'avevo proprio considerata.
Ma a me mi è venuto a mente perché il collegamento di ieri di Antonino ha detto ci vediamo alle 4 e io ho detto ma a che ora sono qua? E allora lui mi ha spiegato che loro stanno un'ora in più. Credo che abbiano lo stesso fuso di Atene.
Sì.
Altri 2 minuti e io mi squaglio.
No, che squaglio. Squaglio che?
Io non ho l'aria condizionata qua, hai capito? Io sto nel forno.
Ok, no. L'ho messo dentro uno studio congelatore qua.
Io per andare al fresco mi devo fare un'ora di macchina da qua.
Ma risolviamo, scrive Antonino, si è bloccato internet.
E va bene, dai, non è un problema.
No, Luana,
andiamo a 2000, non ti preoccupare, andiamo a 2000, facciamo velocissimo. Non mi facete domande, Andrea?
No, io non voglio sapere niente.
Qualunque domanda ce la risolviamo tra di noi.
Ve la faccio dopo, ve la faccio
ce la facciamo dopo.
Vi posso aggregare a questa considerazione?
Ma no, ma perché questo callo che fa? Io perlomeno mi metti i piedi dall'acqua.
Ma tu, scusate, faccio una parentesi. A proposito di questo caldo che fa, ma tu hai capito che mi sono dovuta andare a piare mia figlia che si è sentita male? Tra virgolette, meno male, perché sennò io mo alle 3 stavo là. Mi sono pure imbriagata con gli orari. Cioè, qua a Napoli, cioè dove sto io, stanno veramente 37 gradi.
Ma io non esco da
Puoi venire a casa mia 2 giorni, ti metto al fresco.
Ma è una cosa allucinante.
Sabato e domenica, venite a me, mangiamo in giardino sotto una frasca.
Quando vengo? A fine luglio.
Hanno fatto?
No, non ho fatto niente ancora. Ha detto che mi ha scritto Antonino.
Oh, io vado di nuovo a bermi un bicchiere d'acqua. Voi state qua e dite che io
Non risolviamo, si è bloccato internet.
Sì, risolvete, dite che io esisto.
No, loro risolvono, niente. Io ho risolto già.
Good afternoon, everybody. I'm extremely sorry for the delay. I hope that you can hear me. Can you confirm if you hear me, please? Any of you?
Yes.
Great. Thanks a lot. And sorry for the delay. We had a problem with the connection. And thanks for your patience. I would like to open the session, if you agree, and if you're all ready for that. And I would like to invite the first presenter, Michalina Monaco, please, to present her work with the title Geometrical Proportioning of Masonry Arch Bridges. You can share your screen, please, and the platform is yours. Thank you.
My screen is just shared.
Yes, you can see yes. That's okay. Thank you very much. So the microphone is
Good
here.
afternoon. May I begin?
Sure. Please. Thank you very much.
Okay. Good afternoon. I'm Michela Monaco, and I come from University of Sannio in Benevento, a small city in southern Italy. And my paper regards geometrical proportioning of masonry arch bridges. Masonry arch bridges have been built since the earliest civilization from in Lower Egypt, in Mesopotamia, and a masonry arch has been always the solution to bridge a gap. Here is a small catalog of masonry arch bridges from my homeland. And they are, I have chosen all this because they are actually in service. As you can see from the bottom left image, in which there is a truck
going across the bridge. So if a very small province like Avellino is, you will see the red part of Italy in the bottom right image. You can have information about how much they are diffused in all the territory. And in fact, they have been actually part of the railway and road network, and in some cases they are part of cultural heritage. The analysis of these bridges before the development of static methods were based on geometrical rules and empirical formulas were the only design methods at the time of the constructions. And but now live loads are heavier than those foreseen at the age of realization. And what about the design of these bridges? Here is a small catalog of empirical formulae from the first one by Leon Battista Alberti in the Renaissance period. There were the first relations were only proportional relations that take into account the dimension of the thickness of the crown as a part of the span, as a part of the span. But these relations are too not too safe for large span and unsafe for very small spans. But if you go to a Delhi, you will be able to find a wide set of geometrical formulas for masonry arch bridges, which take into account the relation between crown thickness and span. But so after Perronet in the 18th century, the most used relations were a sort of linear polynomial relations. But we have to wait until Gothi, the last ones, to have distinct relations for distinct ranges of spans, because in general the linear relations give very large thickness in case of large span. So they are safe, but not able to represent a good structure, because the thickness of at the crown is too high. So this is to represent the Delhi. But the Rio Carnival for the empirical formulas can be emphasized, taking into account the formula 19th century formulas. And in this case, we found for the first time difference for shallow arches and circular arches. But if you look at the Dupuy formula, you will see that that the thickness at the crown is can I go? Yes, the thickness at the crown is 0.15, is lower for shallow arches than that for the circular arches. But so the phenomena of stability are not taken into account by this formula. And as the time passes by, we can see that the complexity of the relation increases, and according to the scientific development. Here I have put in evidence the relation by Dupuy to consider the fact that small thickness for low-rise arches is perhaps not so safe as it could be at the first glance. But nevertheless, several arches built with these proportions are nowadays in service. So what's the solution? The solution is the same of the bumblebees. Because bumblebees, according to the law of physics, cannot fly, but they don't know. So a bridge built with a formula by Dupuy per a shallow arch perhaps has the contribution of spandrels and all the elements of the bridge. But if we make reference only to the arch, perhaps it is not so safe as it seems. So this is a small representation of the variation of the crown thickness with the span. All the red dots are real masonry bridge proportions reported in the book by Baker. As it can be noted, almost the totality of them is present crown thickness in the range under the Perroni formula. The only particular case is that of the old bridge at Pontypridd in Wales, but this is only a pedestrian bridge and it has been designed as a pedestrian bridge. This one. The dark blue dot represents a Roman arch bridge in Pont Saint Martin. This too is a circular footbridge, actually in perfect conditions, while the light blue dot refers to another Roman arch bridge in San Mango sul Calore in southern Italy. And as you note, its proportions are far above the Renaissance relations that are the most severe proportions for the bridges. So we have to think that Roman engineers designed arch bridges according the local workmanship and according the material availability. So it is impossible to force the proportion they had into relation that do not take into account all the aspects the Roman engineers considered, because workmanship is an essential element of the quality of the bridge. Dunque, vediamo un po'. Yes, this one. Here there are the Séjourné relations for depth at springing. This is the relation for low-rise arches, and this is for deep arches. And these relations calculate the thickness to the sections corresponding to 120 degrees, because for Séjourné and other French authors, the remaining part of the bridge, or this part under this section, does not behave like an arch, in general due to strong baking. So, in general, material strength is not a key point in a stability analysis, because major cause of global failure is loss of equilibrium rather than material failure. In the case of Mostar Bridge, for example, this has been a particular case because restoration has been done merely by rebuilding. So, I have used the Hyman method to analyze the arches with geometries defined by the empirical rules I've shown to you a moment ago, and considering the Hyman method considers all these hypotheses. In general, it is not said that the first three are always considered. Not, the material has no tensile strength. There is no sliding among the voussoirs. There's infinite compressive strength. Geometrical nonlinearities are absent. Infinite Young modulus. The condition of rigid abutments is in some cases has been removed, but the important condition is there is no baking. The surrounding fill and spandrels act as dead vertical load, and no collaboration exists between arch and spandrels. So the spandrels are not kinematic restraints for the collapse mechanism of the arch that is present when the line of thrust is touches extrados or intrados of the masonry arch. In this case, the failure mechanism is that due to the self-weight, and so the number of hinges present are 5, while according to the Hyman approach, at least 4 hinges will form before the collapse. So the analysis according to this method has been conducted with an iterative method, considering as loading scheme the self-weight supposed constant in all the analysis, and a single point force whose position is defined by ratio A over L. It has been considered, with the except of the point load in the crown, a collapse mechanism with 4 hinges. Two of them have been considered fixed. This one, perhaps I have, yes. This one and that at the abutment in the opposite side. And the work equation has been considered as equilibrium equation, and the final check has been made by verifying that the thrust line lies in the arch and touches extrados and intrados in the chosen section. This is one of the constructions. So all the analysis have been performed on the arch dimensioned with the empirical formulas and related to the upper limit of Sejourné formula, since it gives a reasonable factor of safety. The Sejourné limit is reported in the sensitive analysis with a red line. Here, as you see, the crown in this case for this formula is too thick for large spans and unsafe for small spans. The Perronnet formula gives similar behavior, but all the bridge is all the loads are under the Sejourné limit. And the Cauchy formula is considered in this, and this is the analysis with the Sejourné formula. And as you see, the limit load is somewhat independent on the span length because all the curves are superimposed. Here is the summary of the sensitive analysis, and I have considered the limit load, the same analysis for Panza-Martin, the Roman bridge we have seen before, and it is a bridge in which there is a low crown span thickness ratio, the safety degree in this case is comparable with those obtained by means of the more ancient formulas. You see, this is a 16th century for 30 meters, and Pont Saint Martin has a span of 34 meters. So we have only to think that Roman engineers were able to understand the masonry arches without considering empirical formulas. So even though the construction of masonry arch bridges is not part of our students' training, nevertheless, it is necessary to make intervention of maintenance and repair, and so the principle and the criteria on which the design process was based have to be known to an engineer, to a practitioner. And geometrical rules seems in general non-conservative, but they do not take in consideration the contribution of all the part of the bridge. And limit analysis has the same limits in general, but experience and tests performed on existing structures confirm their good health and their capacity of carrying loads strongly different from that envisaged at the age of the construction. So I would like to conclude with a masonry bridge I walk across every morning. I hope that a complete understanding of these structures could be possible to have the minimum possible interventions and to preserve them for future generations. Only a small note, you will see our banknotes. I hope that the bridges we see every day in our hands will remind us to be builders of bridges and not walls in every sense. Thank you.
Thank you very much for your very interesting work. So if there is any question, I first can ask the people who present in the room if you have any question. Otherwise, those who attend online, you can unmute your connection, and then if you have any question, you can ask. All right. I just have a general question. Thank you very much. First of all, you have presented several real bridges. Just out of curiosity, I wanted to know if these failure mechanism that you address, like generation of hinges, also appeared in the real cases that you mentioned, and or not. This is what we expect them just when they are on their.
I do not hear. I allowed my microphone.
Okay, can you hear me now?
Yes, now.
Okay,
yes,
sorry.
now.
Yes, so I tried to talk a bit louder. I just asked that you have already shown lots of very nice and interesting real case studies. I just wanted to know if the hinges has been observed in these actual cases, and or this is
no, they are perfectly in service. They work every day, and they have traffic on them, and they do not present structural problems. So this is my fear. If you analyze this bridge, perhaps they are not able to be safe. but they are in service since the first year of last century.
Wow, amazing. Yeah, that's
So,
really
so
amazing.
I am sure the Roman bridges are pedestrian, and the Hannibal Bridge, the third one, is in an archaeological park, so it's not there are not load on them. But the bridges I presented in the this one, I hope they no, non c'è la condivisione. I'll show to you these bridges. These bridges.
I think yes. I don't know if your screen is shared because I just
Yes.
can't. Ah, yes, perfect.
These bridges are in service.
Mhm.
Do you look at this? There is a truck on the bridge.
Yes.
So they work every day, and they have. Look at these. These are parapets. Oh no, these are parapets, and here there is the road. Here, this bridge is a railroad bridge, and this one is for a road. So they are. This is 1 kilometer from my home, so I know it I know it very well. They work, and luckily they have not been restored until now.
Oh, wow. Great. Wow, that's impressive. Really, really impressive. Perfect. Thank you very much. Because we are running out of time, I just want to directly go to the second presentation. The title of the paper is The Effect of Localized Damage on the Structural Stability of Masonry Arches. And I would like to ask the presenter to, I just know the author's name, but the name of the presenter is not clear to me, but please.
It's me,
Okay,
Luciana
great.
Di Gennaro. Okay.
Great. So perfect.
Do you hear me?
Yes, I can hear you very well.
Okay.
Thank you.
Perfectly.
I'm sharing the screen. Do you see it?
I can see the screen. Thank you.
Okay. Thank you for giving me the occasion to present our works, authored with Professor Maria Teresa Guadagnolo and Giorgio Frunzio from Department of Architecture and Industrial Design of University of Campania, Luigi Vanvitelli. As is well known, masonry arches are iconic elements of historical infrastructures, commonly found in viaducts, aqueducts, and monumental architecture. And due to several factors, among many, the excessive loads, services loads and stresses, environmental degradation, seismic events, foundation settlements, vegetation-induced damage, material loss, and so on, a significant reduction of structural safety may occur. And the proposed study focuses on assessing the effect of structural stability of one of the possible defects occurred. In particular, the damage considered in our study was modeled as an intrados local reduction in thickness, and a specific load condition was analyzed, where the arch is subjected to the weight and to its own weight and the horizontal forces. This condition, as known, leads to the formation of a 4-inch collapse mechanism. And to better understand the influence of thickness localized intrados reduction, a group of different arches was studied by means of a parametric procedure based on the variation in height and thickness within preset ranges of variation. The study moves within the limit analysis theory, adopting a kinematic approach with respect of the Ayman hypothesis. And in this slide, you can see the hypothesis related to the analyzed load condition and the assumptions of the procedure. The weight remains constant while the horizontal load increases according to the multiplier lambda. And the failure mechanism involves the formation of 4 hinges, with the first block remain fixed and 3 kinematic blocks interposed within the 4 hinges. Clear, the images refer to horizontal forces acting from left to right. A further assumption was that the thickness was constant along all the profile or the whole profile of the arch. According to the assumptions described before, we can obtain the collapse multiplier by applying the principle of virtual work, computing the work of the vertical and horizontal components of the loads and their relative displacement fields, delta UV and delta UH, in the slide. So lambda can be expressed as the opposite of the relation between vertical and horizontal work. Just to recall, the kinematic theorem states that the collapse multiplier corresponds to the minimum value among those associated with all possible failure mechanisms. For the specific loading condition, the different mechanisms are characterized by the variation of the theta angles within specific ranges established in literature. So theta 1 varies between 15 and 75 degrees, theta 2 between 30 and 90 degrees, and theta 3 between 19 and 165 degrees. The collapse multiplier lambda is thus determined through a constraint minimization procedure in which the constraints represent the geometric compatibility conditions between consecutive hinges, and you can see the field omega assigned and that represent the constraints, and the difference between 2 consecutive hinges has to be measured than 15 degrees. The analysis was conducted in a discrete domain with each theta angle vary incrementally by 15 degrees. So theta 1 is represented by, and theta 2 are represented by 13 elements, and theta 3 by an array of 16 elements. So the analysis focused on a masonry arch with a fixed span L, assumed of 6 meters, while systematically varying the rise h and the thickness t. The rise h varies between a quarter of the span, we modeled an elliptical arch, and the half on the span, represented in the slide by h with 5, that represents the round arch. The thickness T was obtained by means an empirical formula as a function of the empirically derived parameter A that varies between 0.15 and 0.18. So for each combination, for each pair of H and T, the collapse mechanism was evaluated as a function of the couple HT, and we obtained a field, a matrix of 5 dimensions. In the left part of the slide, you can see the minimum H and thickness H1 and T, the corresponding to the pair H1 and T1, and the maximum we call the maximum configuration that corresponds to the round arch with the maximum possible thickness considered T5. We have imagined that the damage can be modeled as the definition of three parameters, the intensity, the extension, and the position. In particular, the intensity and the extension in our study was fixed. The first was assumed as the third part of the thickness, and the extension was modeled by a sort of angular distances. So we modeled it as the initial angles phi with I, and the second one posed with an increment of 15 degrees. The variation, the position vary along all the introducts of the arch, and the variation of the position was computed throughout the parameter phi with I. Sorry. That varies in a discrete array of 31 elements, equally spaced by 5 degrees. So this parameterization enabled the systematic assessment of how defect placement affects the collapse multiplier lambda. So a numerical procedure developed by Wolfram Mathematica was developed to systematically assess the sensitivity of lambda. H and T vary, as explained before, and each triplet of theta angles defines the angular position of the hinges in the 4-block collapse mechanisms. And for each pair I and R that are the indices corresponding to H and T, the rise and the thickness, representing the discrete values of rise and thickness. The kinematic blocks are geometrically defined, and their properties such as area, center of gravity, and weight are computed in the procedure. So for the undamaged condition that you can see on the left part of the slide, lambda is computed as a function of 5 parameters represented H, T, and the ordered triplets of theta angles, while for the damaged condition in the right part of the slide, lambda is also a function of the position of the defects phi with I, becoming a 6-dimensional matrix. The geometrical compatibility in both conditions was ensured by a Boolean matrices B that de facto filtered the lambda spaces, deleting geometrical incompatible cases, such as the cases for which theta 2, for example, is minor than theta 1. In this slide, you can see the results for the undamaged conditions. The behavior represented in the graph highlights that distinct structural influence of we have a distinct structural influence of the two geometric parameters. Increasing the thickness T, we can observe the systematic rise in the collapse multiplier across all configuration, confirming that thicker arches are more resistant to horizontal forces. In contrast, an increase in the rise H is associated with a reduction in lambda, indicating that flatter arches perform better in terms of structural capacity under lateral action. The slope of the linear relationship with lambda increases as h decreases, indicating that the structural capacity becomes progressively more sensitive to thickness variation in more diminished arches. And this suggests that for a low-rise configuration, even small reduction in T can lead to significant losses in load-bearing capacity. And in this slide, you can see the results of the damaged condition. Each graph corresponds to a specific cage, a specific rise. The analysis identifies for each graph, for each case, 3 local minima of the collapse multiplier lambda. For 2 of these occur always at damage in 15 degrees and 175 degrees, corresponding to damage located at the springings, which are sure zones of structural vulnerability. And a third minimum can be observed in each graph within the second kinematic block in the interval between 115 degrees and 135 degrees. As the arch rise increases, this critical damage position shifts progressively towards the crown, indicating a shift in the internal equilibrium mechanisms. So, in conclusions, the analysis demonstrated that the arch thickness surely plays a crucial role, especially in flatter arches, as it directly affects their ability to resist the horizontal loads. As for the undamaged condition, clearly. On the other hand, as the rise of the arch increases, the geometry becomes the dominant factor governing the structural behavior. As for the damaged condition, the most critical position of the damage were identified for each geometrical condition analyzed, and in particular, the effect at 15 and 165 degrees is represents a criticism in the for the structural safety of the arch, and the range between 115 and 135 degrees represent another criticism near the crown of each arch analyzed. Clearly, this is a quick assessment procedure that avoid complex modeling complex models such as FEM or DEM models. This could be a practical tool for engineers or for practitioners to a rapid assessment of the structure or the safety of these types of structures, especially in the case of post-earthquake inspections or for for intervention to decide interventions in large scale conservation efforts. Clearly, this is an early study, and we hope we can further improve our procedure, extend the analysis to a broader set of arch geometries and configuration, investigating also additional loading scenario beyond the horizontal forces, and evaluating other elements such as the influence of backfill conditions on the arch stability. Thank you for the attention.
Thank you very much. Very interesting. Before jumping to the question part, I would like to kindly ask all the other presenters, like attendees, apart from those who present, please to mute their meeting session, please. Thank you very much, because sometimes there are some confusion between the sounds and in the background. Thank you very much. That was very, very interesting paper. I would like to ask if there are some in-person questions on that topic. Okay, that's nice. Sorry? Yes. If there is any question online, you can now unmute, and then you can ask your question. If you want, you can also write it in the chat. So I'm sorry, because I am just trying to also a little bit to speed up the meeting. That's why probably, yes, I'm like a bit talk fast. But if you hear me well, I wanted to just have a very, very quick question. And that is that you mentioned, so this work is about it apparently shows that when the height of the arc is are low, so that the rise of arc is lower, then the resistance against the lateral forces is higher. I just wanted to know if the lateral forces or the behavior and movement of the supports also is included in the overall
procedure.
analysis. Yes.
No, only the multiplier of vertical load of the weight of the single ashlars.
Okay.
We have to improve in the future the procedure. This is an early study to better understand the influence of the specific to analyze the geometrical factors.
Sure, interesting.
We have to improve it with other parameters that surely influenced the structural behavior.
Yes, thank you very much. Thank you. So we just moved to the third paper, third presentation. The title is Seismic Performance of Irregular Buildings Through the Continuous Air-Based for Stress Singularities Method, which I believe Andrea Montagni will present.
Do you hear me, and do you see the screen?
Sorry?
Do you see the screen?
Yes, I can see the screen. Thank you very much. Yes, please.
Okay, so thank you for your introduction. This work is made in collaboration with the...
Andrea, I think that we cannot hear you very well. If you just move a bit the microphone.
Do you hear me?
Yeah, that's perfect now. Thank you.
Okay. And so this work is in collaboration with Francesco Fabrosino from Pegasus University, and it's entitled The Seismic Performance of Irregular Buildings through the CAS Methods. During this presentation, I will introduce some preliminary assumptions for measuring material. Then I will introduce the boundary value problem and this variation of formulation for measuring structures. Then I will speak about the continuous area-based for stress singularities method, and I will frame it in the context of limit analysis for measuring structures. And finally, I will show some examples. First, concerning measuring material. Usually, measuring material are represented through rigid blocks where deformations are allowed only on blocks interfaces. and blocks are usually considered as rigid, without sliding between each block. This fosters the development of block-based computational model, above all the distinct element methods. However, we see from reality that fractures inside imagery structures happens not only at blocks interface but also inside blocks, and also to reproduce with high fidelity the block structure of memory can be highly computationally demanding, and this is the motivation for which we move to a continuous model. Therefore, what I am presenting a continuous model for memory, which is represented by a boundary value problem, which is described by equilibrium and kinematic condition in the interior of the domain, by some boundary condition concerning the emerging stresses and boundary displacement, and the constitutive relation that in our assumptions are represented by the Hyman's hypothesis. That is, stress can be only compressive, the material behaves as rigid in compression, that is, deformation can be only extensional, and there is no sliding and no energy dissipation. The solution of such a problem is a triplet of stress, deformation, and displacement, which comply with all these conditions. The same problem can be reformulated into a variational formulation through the introduction of two different functional. A displacement-based functional, that is the total potential energy, which is a functional of the displacement field, and the total complementary energy, which is a functional of the stress field. In this case, the solution is represented by a triplet of stress, deformation, and displacement field, which minimize simultaneously the total potential energy and the total complementary energy. We focus especially on the total complementary energy, developing a force-based method. In this case, we want to minimize the total complementary energy that under the Hyman assumption is a linear functional under the equilibrium, internal and boundary equilibrium, and material compatibility. The set of these three assumptions defines the so-called set of admissible stresses. We can also introduce a scalar functional, that is the Airy stress potential, which is defined such as the stress are function of the second derivative of this Airy stress potential. If we introduce this formulation in the equilibrium equation, we can see that the internal equilibrium is automatically satisfied. Therefore, we have to translate the material condition from a condition on the stress into a condition to the Airy stress potential. Therefore, if the stress is negative semi-definite, the Hessian of the Airy stress potential is negative semi-definite, meaning that the Airy stress potential is a concave function. Therefore, we have to translate the whole problem onto a problem in terms of the Airy stress potential. Therefore, the internal equilibrium is automatically satisfied. The boundary equilibrium transforms into a function of into requirement or boundary condition of the Airy stress potential on the boundary values and of the boundary normal gradient, and the material constraints is described in case of the Airy stress potential by the requirement of concavity of the Airy stress potential in the whole domain. Now I move to the introduction or continuous of the CAS method, which is, as said, a force-based approach. First, we consider a discretization of the domain into quadrilateral elements. In this case, I start from square or rectangular elements. Plate type elements, that is, nodes are provided with 3 degrees of freedom, the value of the reference function and its first derivatives, defining a C1 continuous methods. C1 continuity means that we are restricting to smooth functions for the stress potential. That is, we are assuming that the stress are regular, but we hope that through this method we can model also eventual stress singularities. C1 continuity does not allow for continuity of the second derivative of the stress potential. That means that stresses are not defined on nodes, and this is the motivation for which we define stressing on internal nodes of our discretization, and the stresses can be computed in terms of the nodal degrees of freedom through linear operators. All these formulations can be extended onto generic shaped quadrilateral element, and we can even compute the stresses through a mapping between parent element, square element, into the generic shape real geometry element through a projection of the Hessian from the covariant reference defined on the quadrilateral element onto the Cartesian direction. Then we can discretize the boundary value problem simply by the boundary conditions are expressed through linear equations with respect to the nodal degrees of freedom, while the concavity of the research potential is expressed through conic inequality constraints. Therefore, we can apply this on the minimization of total complementary energy of a structure, in this case, the wall of the church of the Pietà dei Turchini in Naples under soil settlements. And we see that we are able, with this method, to model stress singularities that occurs after soil settlements for structure with generic shape. In this case, we have the presence of arches and doors, holes, and so on. But this method can be framed also in the context of limit analysis, that is, to compute the stability of the equilibrium of a structure. In particular, we can compute if a structure is in equilibrium, if there is at least one static solution under the given loads. That is, we can increase eventual non-permanent loads until it exists at least one equilibrium solution. That is, we want to maximize the load multiplier lambda until an equilibrium solution exists. We can reformulate the boundary value problem by introducing the load multiplier into the boundary equilibrium, and so considering a permanent part of the loads and a variable part of the loads through the load multiplier, and reply the problem. So we want to maximize lambda until a solution exists. We can translate this into the area-based, let's say, formulation, and apply this using the CAS method. Here we are studying the case of a panel under a concentrated load on the top. We see the formation of two diagonal stress bands, which represent stress singularities. And so we here see the capability of the method to reproduce also stress singularities, but we can increase gradually in horizontal loads and see that the internal structure changes as far as we change the applied load on the structure. If we increase the horizontal load, finally we get load multiplier 0.45 can be extended until 0.5, and we see that this diagonal band vanishes, and the final internal structure that develops inside the memory panel is represented by an horizontal bar and a diagonal bar until the right lower corner of the structure. But we can apply the same principles to real structure. Here is the case of a irregular shape facade until permanent loads, that is self-weight and applied weight from the top, and bearing loads from the left and from the right side that can be representative of a seismic action, for example. In this case, we see that the load multiplier with respect to the total vertical loads acting on the structure is in this case 0.55 and 0.58. These numbers in particular are representative of the maximum seismic action that this structure can withstand. But we can do this also for the case of two-story masonry structures, and we see the formation of diagonal bands, and in this case, the maximum load multiplier is 0.37. And finally, we come back to the case of the chart of Italy, Turkey, and Naples, and see that for this particular structure, we see again the formation of stress singularities, and finally, we can get the load multiplier that in this case is 1.12. Finally, we have introduced the CAS method, that is a force-based method for masonry structure, that is a fast and robust method to compute the equilibrium solution under self-settlement, and that can be extended to the search of limit admissible loads for unilateral material that can be interpreted as a seismic load for real masonry structure. So I thank you for your attention and waiting for your questions. Thank you very much.
Thank you, Andrea. Always very interesting to know more and more about your study on theory-based method. For those who attend the in person, do you have any question? No? Yes? You can also come here.
Andrea, thank you for your presentation. Just a quick question. What is, in your opinion, when you are now very expert about this method, can you also give us an overview of what are the, if any, drawbacks of the method?
Limitations.
Well, at the moment, there is some issue concerning the application of self-weights for structure of monoconvex, not but all the structures, because you should try to introduce some tricks in the methods to capture the behaviors when in presence of holes, because there is stress potential, there is stress function works fine with domain without holes, but we are working on this aspect to make the method more and more general. And moreover, I think that it would be very interesting to couple this method to replacement-based methods to find to see better the eventual presence of fractures and capture fracture distribution in some masonry structure under strong displacements.
Thank you, Andrea. Just something off topic.
Yeah, okay. Perfect. Yeah.
Today is his birthday, so we can.
Oh, Andrea's birthday! Yeah, happy birthday, Andrea.
Yeah, thank you.
Yeah, great. So, is there any like question among those who attend online, or?
No, only the happy birthday to Andrea.
Thank you.
Great. Andrea, I also have a super quick question.
Yeah.
You mentioned about mapping from like square shape to any quadrilateral geometry, right? It's
Yes.
about mapping one type of mesh to another type of mesh. Is that what you meant, or?
It says that in case, for example, of a structure like this, for example, of course, you cannot mesh it with rectangular elements since it's the present of axis. So to calculate the curvature in internal points, you cannot do it directly from
Yes.
a generic shape. So you make the calculation into a parent element and then you transport it onto the real geometry, like what happens in standard isoparametric elements.
Okay. Okay.
The problem is that in standard isoparametric element, you don't need to compute the curvature, while in this case you need to do it. And so the development of this is a little bit more complicated, but you
Yeah.
manage it with the same philosophy of isoparametric element.
Makes sense. Makes sense. Thank you very much. Thank you. So we now are ready to move to the last presentation of today, which the title is Area-Based Form Finding of Purely Compressed Masonry Shell Under Vertical and Horizontal Loads. And I think Sam Cooking will, yes, present the work. Please go ahead, Sam. Thank you very much.
Thank you. Can you see my slides okay?
Yes, I can see. Thank you.
Great, thank you. I'm conscious that I think I'm the last presentation of the day, so I'll try not to keep you too late. I'm happy to be presenting online this work, which is it's a collaboration with a few authors, as you can see, but really it's Luigi I want to highlight, who is the PhD student who did the machine learning on this project, which I'll be talking about today. So this is Luigi's work. So our overview of the presentation, I'll go quickly through membrane equilibrium analysis, which forms the methodology behind the form-finding procedure we use for compression-only shells, and talk a bit about how there is a computational bottleneck around the constrained optimization step in that form-finding procedure, and some techniques around machine learning regression algorithms which Luigi trialed to try and tackle these computational bottlenecks, and then some directions we're taking this forward in the future with around physics-informed neural networks and non-convex optimization. So very briefly on membrane equilibrium analysis, a lot of you will be familiar with this already. It's the idea that as opposed to a 2D thrust line, we're looking for a 3D thrust membrane.
Sorry, Sam, excuse me if I interrupt. Are you now moving to the next slides, or still you're in the because
yeah.
you still can see the introduction, like the first page. Am I right?
Oh, I see.
Yeah.
Let me try again. Can you?
Oh yeah, now I can
you see a
that.
different slide now?
Now it's on slide 5. Am I right? Yeah.
Yes, I think that's right. And
Okay.
Can I just check if I go to the next slide? Do you see a different slide now?
Could you please do it now and I check?
Yeah. Can you see a different slide now?
No, still it's on a slide 5.
Okay. Well, maybe I'll just present in this view. If you can see, if I go between slides like this, can you see that?
I believe that's the best way, yes, because now I can see the next one. Thank you very much. Yeah.
No, that's okay. I will try to make the slides a little bigger if I can. So that this is as big as possible. Okay, so hopefully you can see a picture of a vault with a membrane inside it on this slide. So you'll be familiar with the membrane equilibrium analysis. We're looking for a three-dimensional thrust membrane inside the vault, and we use Bucher stresses to express the generalized membrane stresses on the planform. So we go from generalized stresses T to a planform stresses S using the Jacobian, and yeah, that means that we can express the equilibrium in terms of two scalar functions for the stress potential and the membrane height. Depending on which of these we choose as the unknown, we can either assess an existing structure or find a new structure. And by using an area stress potential, equilibrium reduces to one transverse equilibrium equation. So if I go to the next slide, transverse equilibrium under vertical loads only, we can be expressed in this way. We're using common notation for derivatives here. And capital F is the area stress function, little f is the surface of the membrane, so describing the membrane height over the domain, and P are the vertical applied loads. And we can solve this equation using Dirichlet boundary conditions for F, and those will often be a convenient type of boundary condition to use because we'll have some input geometry that comes from an architect's sketch, and we can choose the boundary conditions from the sketch to control the problem. If we introduce horizontal loads, just changes the equation very slightly. We can still use the same approach, the inverse approach, to do form finding, where we assign a concave area stress function and check if the corresponding membrane F is contained within the thickness of the fault. And essentially, we're looking for this light blue area at the bottom of the graph. We want to assess a structure that remains below the threshold of activating a mechanism, even if we have some appreciable horizontal loads. And we can choose a number of different parametric area stress functions to do this analysis with. The more complicated the area stress function, the more refined the analysis, but the more challenging the computation might be in the constrained optimization to do form finding. And as I say, we use the Dirichlet type boundary conditions, which we can import from an architectural sketch directly, and those can control the boundary conditions for the problem. And if we want to solve this using a finite element formulation, then we've used the Phoenix computational package in Python. And of course, to do that, we need to translate this into a variational form. So our equilibrium equation for vertical and horizontal loads gets multiplied by a test function integrated over the domain. And then we end up with a variational form of the equilibrium equation here for vertical and horizontal loads. So then, having got to this stage, I'll talk now very quickly about the form finding methodology, where the computational bottleneck is, and how we've used machine learning to tackle that. So the form finding procedure in one slide is we are given an initial impression of the architectural form in Rhinoceros. We import that shell. We set a parametric form for the area stress function, depending on how refined we want our analysis to be. So that defines the reference shell and the type of area stress function we're using. And we then perform constrained form finding, firstly under the vertical loads to set a form that we know works under vertical loading. And then we introduce the horizontal loads in addition, check that we end up with thrust membranes under each loading configuration that remain within the shell. And then we can evaluate the stresses and check that they're reasonable. So if we've solved this using a direct constrained optimization, then we import the reference surface from the architect, we import the boundary conditions, we perform the constrained optimization with a more simplified form than what I'm showing on the right here, just including vertical loads. That gives us a thrust membrane that should be fully concave in accordance with the constraints on our optimization, and which satisfies the boundary conditions of the original problem. So we know that's a solution under vertical loading. We set that as the reference surface, apply horizontal and vertical loads, and then check that the isometric volume V iso that we obtain, which is the overlapping envelope of all the thrust membranes we find, can be contained within the thickness of the designed vault. And if not, we slightly adjust the design. But there can be a number of issues with particularly a high parameter area stress function trying to do that constrained optimization. You might suffer from local minima, it might not converge. So another way that we've started doing this, and this was Luigi's idea, was to use machine learning regression to learn effectively the mapping between randomized parameters for our area stress function and the form that corresponds to under the boundary conditions we're interested in. Once we have enough simulations to capture enough possible variations of the area stress function parameters, then we effectively have machine learning trained model, which we can use with our actual reference surface for our actual design to estimate optimal area stress parameters. So Luigi tried a few different regression techniques in this study. He used random forest regressors where the decision trees are trained independently, and those are each trained on a subset of the data, so you reduce the risk of overfitting, and you average all the predictions from your decision trees to reduce the variance. We also tried XG boosts, where it's a gradient boosting technique where the trees are effectively shallow decision trees trained on the residuals of the previous tree, so you over time reduce the variance. And lastly, k-nearest neighbors, which simply calculates the point in your hyperparameter space where your simulation is to the nearest trained data. And that assumes that there's a sort of locality in your training data. So similar input parameters produce similar outputs. As long as that's the case, k-nearest neighbors is a pretty simple technique to use. And we assume that because there's that locality and similar input should give you similar output, we use an inverse distance weighting using the Manhattan distance to control the importance of nearby simulation points in the training set. So running through quickly what that looks like using k-nearest neighbors for the plots. We start with this initial surface, we mesh it, we work out what the density of the shell is and therefore what the load distribution will be. We find the actual applied vertical loads because of course this form is curved in space, so it's not a uniform load that's applied, it varies over the domain. Using the Jacobian, we work out the vertical load, apply that with randomized inputs of our area stress parameters to generate a large number of simulation points, making sure at each step that the concavity is respected by the area stress parameters that have been chosen. And then once we have enough of those, we can input this actual form, and we can form find under vertical loads, and we get, you'll see there's some difference here between the two sets of lines forming that meshed surface. So there is a difference between what we put in and what we get out, which is the red surface. And then using that red surface under vertical loads as our new reference surface, we then perform a constrained form finding under the horizontal loads as well. So we consider three directions for the horizontal loads, choose a horizontal load multiplier of lambda is 0.5 g. And then we get the three different sets of surfaces that you can see here with the following stress and maps. So we can see the eigenstresses here and the stream flows of the eigenvectors. And if we overlay the envelopes that we get from all of those different loads combinations, we get this minimum structural volume that will resist those loads applied in each of those set directions. And repeating that procedure for the three different machine learning techniques that Luigi used, he baselined this against the total volume of material used to resist a given set of loading and found that k-nearest neighbors performed pretty well for minimizing the amount of structural material. And to some extent that makes sense because the problem is quite deterministic and you might very well expect nearby similar input values in your area stress function to give you a similar output. So there's some logic there behind that being the best performing method. Looking ahead to future work, the two main directions to improve the performance of the machine learning will be to bring physics in to some extent. So either physics inspired machine learning, where we use the sort of governing physics to sort of as a weighting in training our models. But they're not imposed as hard constraints. So it's still possible that there'll be some violation under certain conditions. You do need to do those checks still, but it makes it faster to train than a deep learning based method such as physics informed neural networks, PINs, where the boundary conditions of the PDEs are part of the training loss. So it's physically built into the machine training. That's one technique. And then the other technique we're looking at in collaboration with Americo Cunha Jr. is non-convex optimization packages. So the idea being that non-convex optimizers should perform more robustly than the standard procedures for optimization that we were trying initially. And a non-convex optimization that Americo uses is the cross-entropy method. So you have some non-convex function, you randomize the function and sample rare events stochastically. you do importance sampling to find out which of the rare events are particularly important to get an optimal distribution, and then as you sample that over time, you build up a quick view of what your global optimum is. So a quick simulation on a random non-convex function here shows that within a small number of iterations, this method does indeed zoom in on the global optimum. So those are two techniques that are forming ongoing work. And thank you. That was a whistle-stop tour, but hopefully there's a couple time for questions.
Thank you very much, Sam. Very nice presentation, and very nice to see how area stress can be used for form finding of masonry shells, actually. So is there any question in the room? No. Yeah, and virtually? Yeah. So I can just have like the last question, like two questions. The first one, just out of curiosity. You mentioned about the application of machine learning for somehow adjusting the results. But these three methods that you mentioned, for example, came in use for clustering, and those, the first one, I just didn't understand how they have been adopted to get the, like, so this means that the input and output of the three methods that has been used are the same, or they has been used in different ways.
So they were trained in a standardized way.
Yes.
So the raw inputs originally would have been nodal heights for the reference surface, or for randomly generated surfaces. But because that would be very high dimensional, so it would be quite inefficient to train the model on that raw data, Luigi used principal component analysis to reduce the dimensionality. So there was, I believe, the standardized framework he used for that. And then the evaluation of the models was done in a standardized way as well. I think it was k-folds cross-validation.
Okay.
But
yes,
yeah,
exactly.
to be honest, I would need to look at Luigi's notes to be
that was part of the
100%
question,
certain.
but we can leave it here for yes, about the validation. That's perfect. So the horizontal load that you have already mentioned, this is this uniformly distributed, or it is just like pointed lateral force or horizontal force?
So we've considered horizontal body forces initially, so with the motivation of seismic loading.
Okay.
But
So
theoretically, one could use a different form.
Right? Okay, great. Thank you very much. Thanks a lot for all the attendees online and in person. And I wish you have a, I don't know, anywhere on this planet you are now. Just have a good day. And thank you very much, all of you.
Bye.
Thank you.
Bye. Bye.